Okay, we're here with Larry Dobson in the Seattle area of Washington State. So, Larry, tell us about the Gasifier stove that you're working on. Why is it good? What are its special features? What this is building on in terms of your experience? How it compares to industry standards?
That's a long
Question.
topic, yeah. But I've been designing furnaces, boilers, gasifiers from the bottom up, looking at the fundamental principles of heat flow and separation of gasification, combustion, heat exchange, so they can be controlled and optimized. And this has brought me to a design that is quite unique with burners and furnaces that are out there now. I can get real cool exhaust to the point where it condenses the moisture out of the fuel. And if you look at the average, let's say, biomass wood, the average fireplace needs wood that is dried down to maybe 20%, 25% moisture content works the best. I can burn chips and sawdust that have been out in the woods in piles, and you can squeeze water out of them. 2/3 of the weight is water, and get that water condensed back out of the exhaust to give you super high efficiencies and super cleanliness. And there's a lot of parameters involved in that. But this means that most of the waste materials from agriculture and forestry and local tree trimmers and a whole variety of sources of municipal waste, burnable materials can be burned, gasified very cleanly. The gas used for furnaces, for internal combustion engines, and we can compete with other sources of alternative energy as far as cleanliness and efficiency goes. The concentration of energy of a biomass system like mine is really at least 10-fold and 20-fold times the payback period of solar and other systems that are much larger, because you've got a lot of heat involved in the stored biomass that accumulates into materials that are later become the waste stream. Let's see.
About the design for open source ecology, as far as the roundy gasifier burner. Let's introduce that.
Okay, so I have designed a specific gasifier for residential size and a little larger that takes all of these concepts and turns them into the most elegant configuration, which is concentric and spiral shells that feed back the energy into the incoming gasification air, so that the quality of the gas is much higher, and then distributes it out into the heat exchanger in a way that there's maximum utilizing of gravity. Gravity flow is utilized throughout this whole system to the extent that you don't even need a stack to get the draft. The draft is created by expansion and contraction of the gases, which in a heat exchanger that's counterflow gravity stratified, you get the greatest flow patterns next to the heat exchanger surface, which creates a much more efficient heat exchanger. And then it condenses the moisture out of the fuel, out of the exhaust, and you get all of that heat of vaporization back. And that can be a tremendous amount, because for every pound of fuel, say half of it to a third of it is water. And then from the bone dry fuel that's left, half of that turns into water. So you've got, say, 3/4 of your exhaust can be condensed out of the steam back into water, and you get all of that heat of vaporization back. You get much higher efficiencies, up into the 90%. And with this configuration, the gravity stratifies the gases so that when you turn it down, you get higher efficiencies rather than lower efficiencies with the present systems, and you get much greater turn down ratios. So you can go from, say, 5,000 BTUs an hour up to 150,000 with one system.
Mm-hmm. How does this compare to industry standards? What's the typical burner or furnace stove?
Industry standards vary all over the chart, and their proposed efficiencies are generally not what they get in real practice. Exhaust temperatures are generally 400 to 600 degrees Fahrenheit, whereas mine are say 130 to 200. And the turn down ratio of most gasifiers is maybe 2 to 1 or 3 to 1, where I can get 20 to 1. Mm-hmm. And the fuel standards that they require are much more stringent. For gasifiers, it's very fuel specific. You have to have dried chips of a certain configuration without fines in them, or you can, and they generally don't even work on pellets. Mm-hmm. So there's a very limited fuel source of what's available out there now.
Yeah. So as far as the building of these, it's not an easy build, but let's see. Talk about. Would you agree that the building? This is a complex device, we can say. Mm-hmm. Tell us about the modularity of it.
Well, the modularity of this is a prototype design that will find out a tremendous amount of hard data on temperatures and burn parameters, gasification parameters, that we can design more specifically and hone in on the modularity as well. Mm-hmm. At this point, I have 3 modules that can be replaced and interchanged. The one is the hopper, the whole gasification system, which is broken down into the stainless steel components down in the bottom, and the ceramic components on the top that have the combustion module and the heat exchanger to preheat the air. And those are 2 separate configurations. You can replace the ceramics. And then the heat exchanger is a spiral cylindrical path that the hot gases take to, in this case, it's heating water.
Can that be taken right out of the whole burner?
Yeah, that can be removed and replaced with a different module too.
Mm-hmm. A spiral one, but you can't do, for example, a monotube in there. That's with the present configuration.
Yeah, the monotube does not lend itself to the specific directive of creating a flow pattern that has to go in a spiral configuration. As the hot gases cool, they go down and and separate by gravity, so that you have the hottest gases recirculate, so to speak, in the convection channels, and the coolest gases go down next to the heat exchanger surface, where the water is going up next to the heat exchanger surface, and you get maximum heat transfer.
Yeah.
So the tubular configuration doesn't lend